All right, one more example, and then we'll be done with class 14, or week 14. Here is a car, and we want to find the normal modes of the vibration of an automobile simulated by the simplified 2-degree freedom system with the following numerical values. So let's see, let's take a look at what the book has. The book doesn't have a lot. All right, so I never like these kinds of solutions where they just kind of jump through a couple things and they don't really work through them. I'm going to get a different answer to that, and but that's okay. That's probably just some simple math. Mine's not very far off, in my opinion, but maybe other people's wouldn't. All right, so we have a weight of 3,200. That was probably on purpose so that it would come out to 100 slugs, 32.2. Length of 4.5 right here, and length of 5.5 here. So here's the center of mass of the thing that we'll be using. Got a spring, and it looks like the springs in the upper shocks are much larger than they are, not much larger, but a little bit larger than in the back. Mass moment of inertia, what you end up finding. So this is generally considered the radius of gyration. It's just a way to describe this thing's resistance to rotation about the center of mass. And the overall is long. So that's what the results are going to be looking at right there. So let's take a look at mine. Okay, so I found using their mass the J, C, and this our good friend the radius of gyration, they could be 1,600 slug feet squared. We're going to use the results that we got. I'm not going to run and do the free body diagram again because this was the same one as this right here, right? So using those results right here, we can go ahead and attempt to solve for the natural frequency. So this is a pretty well-established method. There's a little bit of concentration that you'll need to do with that, but here is the two results that we general form, and here's the second derivative of both of those that we can expect. So when placing them inside here, and also let's see, placing them inside here, we could get these second derivatives, or these omega n squares, the natural frequencies, show up right here and right there. And here's an A1 and an A2. So we haven't really violated any rules. We will switch out the omega n squared with a lambda, and I also took that opportunity to stick in the numbers, right? Because we do have values, and I was careful to use the mass instead of use the weight, and here's the mass moment of inertia of the thing, and everything is fairly consistent. Got it down to an equation where I'm going to take the determinant of it. I should have actually made the little determinant. Doesn't have those kinds of bracket things on it, does it? It doesn't matter. And get the determinant of it, so that's equal to 0, and we find out that we have this quadratic equation. I used Wolfram alpha this time and got these two values, and from there we can get the natural frequencies and then turn them into frequencies with units of hertz by divided by 2 pi. It's a little bit off from what the book has. The book has these as 6.9 and 9.06. I don't feel terrible about that. 6.9, and then then this one ends up being 9.06. So I'm a little bit off. The interpretation of what the they went ahead and I'm going to the next step, and instead of using a ratio of A1 to A2, which is essentially what this is, they got this, and it's not non-dimensional. It's inches per degree in this case, and inches per degree. So you could kind of see, get sort of an idea of what's taking place. So they're saying in the first case right here, we're getting sort of a movement that goes up like that, and a movement comes down like that. And then in this case right here, we're getting more of a twisting one. So this has more of a translation aspect to it. This has more of a rotation aspect to it in these two fields. They also go a little bit of a description that we with if you did a 1 degree of freedom, and that here's how far off you'd be. Although this looks like what mine were, right? 7.07, is that what I got? 7.07. Yeah, 7.07. That's interesting. And then they also had 8.92, which is, well, not quite what I had. Let's see, I have a little bit of just trying to mess around with it. I only have the SolidWorks little motion right there. In class, I can bring my laptop and we can hopefully we can mess around with it and lift it up and give it an initial conditions. But a lot of its behavior is dependent on your initial conditions. So there you go. There are coupled systems and mixed coordinates, or mixed coordinates for like x and theta. You can see that by choosing different ones, which is essentially what we've done up here, right? We chose, these are the same problems, but we choose different coordinates. Our first coordinate was picking at the center of mass, which resulted in a coupled and statically coupled. Our next we chose, and we moved it over to this spot, and it gave us something that was dynamically coupled but not statically coupled. And then choosing to go over here far over to the left, we got something that was both dynamically and statically coupled. It'd be interesting to try this problem out and see what the results would be. If you gave it the same initial conditions, and because these are basically the same problem right there. If you look through all three of them, they have all the same features to them. We're just using a different reference point for the motion. So I'm done now. Have a great